Alright, in this video I'm going to be talking about properties of logarithms. And so the first one here is what we call the product rule. And it's going to be property 1, or it's the one I'll refer to as property 1. And notice what we have here is the log of a product, the log base b of m times n, is equal to log base b of m plus the log base b of n. So basically the log of a product is equal to a sum of logs. Quotient rule, here we have the log of a quotient is equal to a difference of logs. So basically these two are opposites. The log of a product equals a sum of logs, and the log of a quotient is equal to a difference of logs. The last one is what we call the power rule. Because it's the log base b of m to a power, we call it p, is equal to p times the log base b of m. So basically we move the exponent to the front of the log when we do the power rule. Now in this video I'm not going to go through the proofs, but the underlying, really the key justification for what makes these work are the rules of exponents. If you actually look at the proofs of these, you'll see these three exponent rules. The first one for the product rule, the second one for the quotient rule, and the third one for the power rule. And another key step in the proof is changing forms, which we've talked about before as being important. You got to be able to go back and forth between exponential and logarithmic form when you're dealing with logarithms and exponents. So anyway, let's go ahead and get started. We're just going to be using the properties. So it says expand each logarithmic expression. So the key word here is expand. And so you'll see what we mean by that. Evaluate logarithmic expressions where possible. Alright, so let's look at example 1. Clearly we have the log of a product, 9 times x. So we're going to use the first rule, and we're going to split this into two logs. The log base, so we're using rule number 1, log base 9 of 9 plus the log base 9 of x. So again, we're just using the product rule. Now if you look at the left here, log base 9 of 9, we need to think back to what that really means. Remember, a logarithm is an exponent. In this case, it's the exponent you put on a base of 9 to get an answer of 9, and that would be 1. So basically 9 to some power is 9, that would be 1. And so log base 9 of 9 is 1, and it'll be plus log base 9 of x. Let's go on to example 2. And if you want to try it before you watch the video, you can certainly do that. It's very similar to the one we just did. Alright, so we're going to use property 1 because we have the log of a product. So we'll break it into the log of 100 plus the log of x. Of course our base here is 10. This is a common log. Note again, when we don't write the base, it's understood to be a 10. So again, this is a 10. So actually we can evaluate this first log. It's the exponent you put on a base of 10 to get 100, and so that would be 2 plus log of x. Alright, let's move on to number 3. So here we have the log of a quotient, so we're going to use rule 2. So it's going to be a difference of logs, the log base 5 of 5 minus the log base 5 of x. Now the order has to be the way that I put it here. So you do have to put the log base 5 of 5 first, and then the minus log base 5 of x. So order is important with the quotient rule, not as important with the product rule, but we normally put them in order anyway. Log base 5 of 5, that should stand out to you as something we can evaluate. What exponent do we put on a base of 5 to get an answer of 5? That would be 1. So it's 1 minus log base 5 of x. Alright, let's move on to example 4. We also have a quotient here, so this is going to be property 2. Be the log of x minus the log of 1,000. And again, our base here is 10. So we can evaluate the second log. Let's see, 10 to the first is 10. 10 squared is 100. 10 cubed would be 1,000. So this is the exponent 3. So it'd be log of x minus 3. Now, it's probably a good idea to put parentheses here just to make it clear that you're not taking the log of x minus 3. All right, let's go ahead and look at example 5. So this will be our first example where we have the log of a power, x to the 7th power, and so we can use the power rule, and we're just going to move the exponent out front. Now, some people like to just do a little arrow like that, but in any case, that's all we're doing is moving our exponent to the front. Let's go ahead and look at number 6. Again, we're going to use the power rule. It's just like number 5. So we'll move the negative 8 out front. Now, example 7 is similar, but it's a little bit, it's going to take one extra step here. And we have to remember that when we see a radical, we can write that using fractions as exponents. Since our root is 3 here, we can write this as x to the 1/3 power. See, the thing is, none of our rules dealt with radicals, but we do have one that deals with powers, and so now we can use the power rule and move that 1/3 out front. All right, when you look at number 8, now we're getting into problems where we're going to end up using more than one of our rules. And in this case, we're going to need the product rule because we have x times y cubed. And we do have y to the 3rd power, and so we're going to be using the power rule. And the thing is, you got to think about this. Can we use either one first, or do we have to go in a certain order? Well, let's look at the the power rule. If you have the log base b of m to some power, so you have a single base to a power, then we can move the power out front. Well, in this problem, we've got that x. So it's we can't really just move the 3 out front because it's not just a power or a base to some power. We've got that extra variable in there. So we actually can't use the power rule. What we can do, though, is use the product rule. So let's go ahead and break it up because we do have the log of a product, x times y cubed. And see, now we do have the log base b of y cubed, so a single base to a power. So now we can use the property 3 and move that exponent out front. All right, so you may want to try example 9. It's similar to what we just did, and then you can watch the video. All right, so we can use the quotient rule here. Again, we can't really use the power rule. You just can't pretend that that 8's not there. Certainly, there's no fraction involved in the power rule when you looked at the actual rule. And so we can use the quotient rule, though. Let's go ahead and use rule 2, the quotient rule. And this becomes the natural log of e to the 4th minus the natural log of 8. And see, now we do have e to a power, so a single base to a power. And so we can use the power rule and move that 4 out front. So we're going to get 4 natural log of e minus natural log of 8. Now, natural log of e, keep in mind that natural log is base e. Let's look at that a little more closely. So our base is e here. So the question here, again, this is an exponent, and a log is an exponent. It's the exponent you put on a base of e to get an answer of e. Well, that would be 1. So the natural log of e just is equal to 1. So this is 4 times natural log of e, or 4 times 1, which is 4. We're going to get 4 minus natural log of 8. All right, number 10. Well, it looks like we're going to need to use the quotient rule here. But again, when we have a radical, we want to go ahead and write this as x plus 1 to the 1/2 power. So I'm going to do the quotient rule, but I'm going to write that expression as x plus 1 to the 1/2 power. So we're using the quotient rule. Log base 5 of x plus 1 to the 1/2 power minus log base 5 of 25. Now we can move that exponent out front using property 3. the power rule. So let's go ahead and do that. And then when you look at the second log there, notice that we have a base of 5. We can evaluate this one. What exponent do we put on a base of 5 to get 25? Well, that would be 2. All right. So you may want to try 11 and 12 to challenge yourself and see if you can get those, and then watch the video. All right, so on number 11, we're going to have to use all 3 of our rules, but the only one we can start with is the quotient rule because we do have a quotient. Now you can't really use the product rule because we basically have to pretend that denominator there doesn't exist, but it does. And we can't use the power rule because there's all sorts of other stuff going on. It's not just a single base to a power. So quotient rule is all we've got, all that we can do to start. Let's go ahead and break this into 2 logs using subtraction. And now notice the log base b of xy cubed, we can use the product rule there and break that into 2 logs. Don't forget, we still have that last one. And then I'm going to use the power rule, and we'll move those exponents in front. And so that's going to be our final answer. Now, I just want to kind of remind you, or kind of just make it clear, when we're expanding like this, which is what we've been doing with all these problems, we started with a single log. And when we get done, notice it's log base b of x, a single value, plus 3 times the log base b of y, which is a single value, minus 2 times the log base b of z. So x, y, and z are just single values, and that's what we end up with when we expand a logarithm. Let's go ahead and look at number 12. Now, here's a problem where we have a fraction, and notice we actually can't use the quotient rule first because the fraction's under the radical. We just can't pretend that radical's not there. So we really need to deal with the radical. So let's go ahead and write this using that as a base to the 1/2 power. And now we can actually get rid of that 1/2 power using the the power rule. So let's do that. And so now we can use the quotient rule. So let's go ahead and use the quotient rule next. Notice I had to so I started with a single log that's multiplied by 1/2, and I'm breaking that log into 2 logs. So I've got to remember that both of those have to be multiplied by 1/2, which we'll do at the very end. Now look inside, our first logarithm has x times y squared, so we can use the product rule to break this into 2. So we get the log, or 1/2 times the log base 3 of x, plus the log base 3 of y squared, minus the log of 13. And so let's go ahead and use the power rule to move that 2 out front on the y squared. So I'm just rewriting that, but I'm going to put that 2 out front. So finally, we can actually distribute the 1/2. That's what I'm going to do. So it'll be 1/2 times the log base 3 of x. And then 1/2 times 2, that's just 1. So it'll be plus the log base 3 of y. And then 1/2 times a minus log of 13. It'll be minus 1/2 log of 13. And that's our final answer there. All right, let's move on. So now we're going to go in the opposite direction, and in this case we're going to do what we're going to condense. So we're going to condense what's 2 or 3 logs into a single log. Now you might be wondering why we're doing this expanding and condensing, and really it comes down to one thing for our purposes, and that would be sometimes when we're working with equations, in particular if we have 2 logs, we can put those together to form 1 log, and when we're solving equations, that's going to make things easier for us. Now, for those of you that may be moving on to calculus, when you get to calculus, you do 2 major topics. You find derivatives and you find integrals. And when you're doing that and you work with logarithms, sometimes one form is better than the other. And so you may condense two logs, or you may expand a single log depending on the situation, whatever makes things easiest when you get to calculus. But again, for our purposes, this is going to help us when we get into solving equations, particularly what we're about to do. So let's look at number 13. Now before we get going here, I'm going to go ahead and write our properties at the top. So our three properties. And so it's clear we have a sum of logs on number 13. So this is certainly property number 1. And so we can write this as the single log of the product of x and 3. And that's just 3x. We normally put the number before the variable. Let's look at number 14. Notice this is a difference of logs. And so basically, if you look at the right side of our second property, we're just going in reverse here. We can write this as the log of a quotient. So let's go ahead and do that using property 2. It'll be the log of x over 3x plus 7. And again, the order matters with this rule, so be careful that you follow the order that the x comes before the 3x plus 7, so the x is in the numerator. Let's look at number 15. Now you might be tempted to use the product rule right away, but I just want to point something out here. Notice in the property you have 1 here and a 1 here. So there's no number there. It's understood to be 1. So we can't really use the property if we have some number in front of the log. So here we have a 5 and here we have a 6. And so we actually can't use the product rule yet. However, we could use the power rule and move that 5 to be an exponent on the x and the 6 to be an exponent on the y. And so we're going to go ahead and do that. So sometimes I like to use little arrows when I do this. So we're using property 3. We're going to get log base b of x to the 5th plus the log base b of y to the 6th. All right, now we do have a 1 out in front here and here. And so we can go ahead and use the product rule. We have a sum of logs, and we can write this as the log of a product. Again, using property 1, we get log base b of x to the 5th times y to the 6th. All right, let's move on to number 16. So again, this is just like the one we just did. Let's go ahead and move those numbers out front to be exponents using the power rule. Now notice the y to the 1/2 power. We can rewrite this and we'll have natural log of the square root of y. And now we're ready to do the quotient rule since we have a subtraction of two logs. And so we get the natural log of x squared over the square root of y. All right, let's look at number 17. We'll start the same way. We're going to use the power rule and move those numbers that are out front. Now let's see, we could start with the product rule. We have the first two there, the ln of x to the 4th plus the natural log of y to the 7th. We can use the power or product rule there. So let's combine those using multiplication and minus natural log of z cubed. So now we have a quotient, so we can use the quotient rule. And let's go ahead and do that. Now I want to show you something here that it's a really nice pattern to notice when you're working with logs. Notice that this term here, actually, yeah, that's good. This term here is positive, and notice the x to the 4th ended up in our numerator in our answer. And notice we also have a positive here, and the y to the 7th power ended up in the numerator. Now here we had a minus, and notice the z cubed ended up in the denominator. So that's a nice pattern to notice when you're doing these. In fact, you could have gone directly here to here if you know that pattern. All right, let's move on. Now on number 18, there's a couple of ways you could do this. You could distribute the 1/2 first, but I think you'll find it's a little bit easier to work inside the parentheses first. And so let's go ahead and use the quotient rule, and we can combine those two logs together into one. Again, the difference of logs can be written as the log of a quotient. Don't forget the 1/2 out front. Now we can use the power rule to move that to be an exponent. So let's go ahead and do that. And of course, anything to the 1/2 power, that's a square root. So again, as you do these problems, you should realize we're doing exactly what we did in those first few problems at the beginning, but we're going the opposite direction. So we tend to do things in the opposite order. All right. So you may want to try number 19. It's a more challenging problem, and then you can watch the video. All right, let's go ahead and do this. We're going to move those powers again. We got the first two there, and you get what I have here. And 27 to the 1/3 power, that's a cube root. Let's go ahead and do this off to the side. Cube root of 27, well, 3 cubed is 27, so cube root of 27 is 3. And notice 5 cubed, that's going to be 125. So let's go ahead and take care of that. We can write this as log base 3 minus the log base b of 3 minus log base b of 125 plus the log base b of 4. Now, we can go ahead and use the quotient rule here, and it'll be the log of 3 over 125 plus the log base b of 4, and then the product rule, and we'll multiply those two together, and you can write it as 4 over 1. We're going to end up with 12 over 125. Now again, I want to remind you that you actually didn't have to do that last couple of steps. Notice here we have a positive. That 3 ended up in the numerator, and the 25, notice here this is a minus. The 125 ended up in the denominator, and since we have a plus here, that 4 ended up in the numerator. It was 3 times 4. That's how we got the 12. So again, you could have taken a shortcut and just gone from here to here if you see that pattern. All right, one last thing. We're going to talk about the change of base formula. So if you look at this, it says the log base b of m is equal to the common log of m over the common log of b. Now on the right side, I could have made both those natural logs. Basically what I'm saying here, I could have any base b, any base, and I can rewrite it as a quotient of two logs where we use either base 10 or base e. So we call this a change of base formula because it enables us to basically evaluate any base log on our calculator by changing the base. Now I'm going to go ahead and show you, well, this is actually the proof right here. So we're going to start right here by letting x equal the log base b of m. Notice that's the left side of our formula. So we can actually change forms, and we get this statement here. So changing from logarithmic form to exponential form, we get b to the x power equals m. Now this next step we haven't really done, but I think it's rather reasonable. We're taking the log base 10 of both sides. And we've learned that we can do the same thing. As long as we do the same thing to both sides, we can do that. That's a basic principle of solving equations. Now the next step, notice all I did was use the power rule and move that x out front. And now at this point, to get x by itself, I'm going to divide by the log base b on both sides. And so finally you get x equals log of m over the log of b. Now keep in mind, we said x is log base b of m. So we're going to replace x with log base b of m, and notice now we have the result we were trying to get. Log base b of m is equal to the log of m over the log of b. So what does that mean? How does that help us here? So for example, on number 1 here, we can write this as the log of 8 over the log of 3. Notice our base was 3. Now we have a quotient of 2 common logs. So you can put this into your calculator pretty much like it looks here. Just make sure you put parentheses around the 8 and the 3. And you should get about 1.893. And I would just remind you that this is the exponent that you put on a base of 3 to get 8. So to check this, we actually could go ahead and take 3 to this power and set it equal to 8. And if you check that on the calculator, you'll see that that's true. Now, because we're rounding, it's not going to be exact, but it should be pretty close. All right. Now, this last one may be familiar to you. We did this earlier. Log base 2 of 5. Actually, we did it in a previous video. We never were able to evaluate this before, but now we can. This is the log of 5 over the log of 2. And if you throw that in your calculator, you should get 2.322. And again, this is the exponent you put on a base of 2 to get 5. So if you want to put that power to the 2, you should get 5, and that does check. All right, and that's the end of this video.